Hi everyone, so in this video we are going to cover on the topic of friction. Okay, this video will be divided into probably two smaller segments, one covering on the concept of dry friction and another one will be covering on the wedge structure. Okay, so stay tuned. Okay, let me give a very simple analogy on friction. Let's say you are walking across a hall and compare the situation when the floor is made of cement and another situation when the floor is made of, let's say, ice. Macam cerita Frozen gitu kan. So, even if you have never walked on ice before in your life, but then you can imagine that it is very slippery to walk on ice compared to walking on cement. Okay, the same goes when you are trying to move or sliding an object on a different surface. It requires more effort or more force to move an object on a cement compared to moving the same object on ice. Okay, such differences are caused by a contact force called friction. Okay, friction is basically a force which tries to resist a movement between two contacting surfaces. If you want to move or slide an object on a surface, you need to apply some kind of force to the object. Okay, that force usually we label it as P to indicate as a pushing or pulling effect. Okay, friction is a reactive force which happens at the contact surface, which is tangent to the contact surface definitely, and it is in the direction opposite to the force that we applied earlier, which is P. Okay, of course lah, it is in opposite direction because it tries to resist the motion caused by P. So some surface would have high friction limit while some other surface would have lower friction limit. So that is why in the example I gave earlier between the surface of a cement and surface of ice, so that is why ice is more slippery compared to other rough surface because of the magnitude of the friction limit. For this chapter, we are going to focus on the concept of dry friction. Dry friction is a situation when there is no lubricating fluid in between of the contact surface. Dan nama pun dry kan, so there are no additional fluid lah to help reduce the friction and whatnot. So now, let us look at how we can construct the ideal free body diagram between the two surfaces by considering the friction effect. Consider an object. Usually we call the object as a body, and the body is landed on a surface. Okay, so an external force is subjected to the object and the direction of force is as shown. Of course, the weight of the object would also be subjected to the centroid of the object. Okay, now if we zoom up at the contact surface between the object and also the floor, in reality, there will be some microscopic irregularities between the surface, meaning that the surface would not be ideally flat. Okay, kalau flat, then there would be no friction at all. Shoo, dia licin je dia jalan macam tu. So, okay, so at the contact point between the surface, there would be an output force called N to balance out the effect caused by the weight of the object. There would also be a horizontal friction force which tries to resist the motion caused by P. So, an ideal free body diagram that you can construct involving frictional force should consist of four main forces. Okay, this is very important. The first one is the external force subjected to the object, which is the P. Okay, the second one is the weight of the object acting on the centroid of the object. The third one is the resultant normal force at the contact surface to counteract the weight of the object. Please notice that due to the microscopic irregularities, the position of force N would not be exactly at the middle of the contact surface. There should be some displacement measured from the center of the contact surface. Okay, that displacement is labeled as X. Okay. Finally, probably the most important one is the frictional force at the contact surface, which is in the opposite direction to the direction of force P. Okay, itu saja. If you apply a low pushing force, the corresponding friction force would be high enough so that the object doesn't move at all, means that it remains in equilibrium. However, as the pushing force increases, the friction also increases because it will try very hard to resist any changes to the equilibrium condition of the box. But at certain point, the F will reach a maximum frictional force in a way that the F cannot tahan the external force anymore, which will cause the box to start slipping. Okay, bukan slipping tidur, but slipping as in mula bergerak. That point when it begin to move, that is the point we refer as the impending motion. Okay, the maximum friction force termed as Fs can be calculated by multiplying mu s with n, whereby mu s is the coefficient of static friction, whereas n is the resultant normal force at the contact surface. Okay, the mu s defines the limits of the contact surface to be in static state. For example, the mu s for metal on ice is within a range of 0.03 to 0.05, whereas the mu s for aluminium on aluminium is within the range of 1.1 to 1.7. So you can see the coefficient of static friction for metal on ice is far lower than aluminium on aluminium. It means that metal on ice will have a lower frictional limit, okay, compared to aluminium on aluminium. So that is why it is easier to move object on ice compared to an aluminium surface. The relationship between the frictional force F and the applied force P can be referred to in this graph. Okay, as long as the applied force is below the maximum static friction limit, Fs, the object will be in equilibrium. It will not move at all. But as it reaches the maximum static friction limit, it will begin to move. And interestingly, as it moves or slips on the surface, the corresponding frictional force will drop. The friction force doesn't disappear, okay? It just slightly drops at a gradual point called kinetic friction, or Fk. The magnitude of the friction when the object is moving tak sama dengan the magnitude of friction when the object is not moving. Okay, so the formula for kinetic friction or friction when the object is moving can be calculated by multiplying mu k with n, whereby mu k is the coefficient of kinetic friction, okay, and n is the corresponding normal force at the contact surface. There are a few problems involving dry friction. Okay, the first one is when there is no apparent impending motion. Maksudnya, if you look at this particular structure, friction is applied to joint A and joint C. Okay, and the corresponding free body diagram is as shown. So, if you look at this particular free body diagram, there are 6 unknowns. So therefore, you have to generate at least 6 equilibrium equation. So 3 equilibrium equation from the first member and another 3 equilibrium equation from the other member. If you look at this figure, point A and point C have different magnitude of coefficient friction. Okay, so at one point it is 0.3 and another point is 0.5. So we are unsure at which point that the impending motion will happen first. Okay, the second problem involving dry friction is impending motion at all points of contact. Okay, consider this single member which is being held on to 2 surface. So there will be 5 unknowns which can be solved with 3 equilibrium equation and another 2 frictional equation. One is a frictional equation for static and another one is a frictional equation for a kinetic case. The third problem involves impending motion only at some point of contact. Okay, so if you refer to this particular diagram, when a force P is subjected to one of the 2 member, so it will either slip at A and no slipping at C, or the other way around. Okay, so that is another problem involving dry friction. Tapi apa-apa pun, this problem is just related to the equations being generated lah, basically. Okay, now we are going to look at different scenarios involving friction. Okay, you know, certain times when you try to push an object, okay, if you do not push it hard enough, the object won't move. Okay, it will stay in equilibrium. But then there are certain times if you apply more force, barulah that object bergerak. Okay, but there are also certain times when you try to apply very high force, instead of bergerak, that object become tergolek or tipping. Okay, so we are going to look at the mechanical situation when such event will happen. Okay, when you apply a force smaller than the friction force, then the body will remain in equilibrium, or in other words, it will not move. However, if you increase the load subjected to the object, then it will reach a point whereby it reaches the maximum static friction limit. And at that point, the body will begin to slip, or it will begin to move. At some point, when the position of the resultant force are shifted right to the end of the contact surface, or when the X reach the limit of the contact surface, this is when the object begin to tip, ataupun dia akan start tergolek gitu. Let's look at the first example. In this example, given that the mass of the crate is 20 kilogram and it is subjected to a force of 80 Newton, subjected 30 degree from the x-axis. Okay, so they wanted to know if the crate will remain in equilibrium, if it will stay static. Okay, so given that the coefficient of static friction is 0.3, so the first thing we need to do is, okay, we know there is a weight subjected to this crate, to the centroid of the crate. So weight is equals to mg, the mass is 20 kilogram, and the g, or gravitational acceleration, is 9.81. So you can easily calculate for the magnitude of the weight to be 196.2 Newton. Now, this crate rests on a cement, okay? Based on the ideal free body diagram of a friction condition, so the force of the friction would act over here, tangent to the contact surface, and in the opposite direction to the P. Okay, and then there is a normal force acting upward to balance out the weight. Okay, please be careful. Make sure that the position of your N and your F is slightly deviated from the centroid. It have a distance of X from the center point of the contact surface. Before we come up with the equilibrium equation, let us just resolve this sangat-bangat punya force into an equivalent X and Y direction. Okay, along the X direction, this force would become 80 cos 30, and along the Y direction, it will become 80 sin 30. Okay, let's think of the strategy required to solve for this kind of problem. Okay, the first thing you need to do is you need to look for the resultant normal force. And then you have to find the magnitude of the friction force. Okay, and when you have attained these two information, you can calculate the maximum static friction limit, whereby Fs is equivalent to mu s multiplied with the normal force N. Okay, so when you get this value, then you can conclude if the friction force that you calculated is less than the Fs, or the maximum static friction limit, then you can say that this crate will be in an equilibrium state. So based on this strategy, our first step is solving for the magnitude of F and also the magnitude of N. So in this case, we are going to apply the equilibrium condition along the X, Y, and also the moment direction. Okay, so applying equilibrium in the X direction, okay, there are two forces in the X direction, which is the 80 cos 30 and also the friction force. Okay, we put that into our equation and we can easily solve for the magnitude of F, and you can calculate it to be 69.2820 Newton. So the magnitude of F is done. Okay, the next step, let us proceed with the equilibrium condition in the Y direction. Okay, so there are three items in the Y direction, which is the 80 sin 30, and then the weight of the crate, which is 196.2 Newton, and also the respective normal force acting upward. Okay, you put all that three item in your equation and you can easily solve for the magnitude of the resultant normal force to be 236.2 Newton. So the N value is done. Okay, before we proceed on calculating the maximum static friction limit, let us calculate the value of x first. Okay, so this can be attained by applying the equilibrium condition for moment. And let's say this is point O, so we want to apply the moment at point O. The main reason why we want to know the value of x is because we want to know clearly if the force being subjected to the crate will cause the crate to tip or slip. Now, let's apply the equilibrium of moment at point O. So, 80 sine 30 force will create moment at a distance of 0.4 meter. And then 80 cos 30 will also create another moment at a distance of 0.2 meter. And the normal force will also create moment at a distance of x. Okay, so we put all these values into our equation, and you know that we already calculated the magnitude of n earlier, which is this 236.2 Newton. So you just substitute this value into the equation, and then you can easily solve for the value of x. Okay, use your calculator and you will get the magnitude of x to be negative 0.0091 meter. The meaning of this magnitude is that, okay, if I were to redraw some part of the crane touching the surface of the floor, okay, if this is the center point of the crate or the contact surface, then the friction force and the normal force are being subjected at a distance of 0.0091 meter to the left. Okay, negative means that it is slightly to the left, just a very small amount lah. What we can conclude from this value is that the location of the resultant force and the friction force is still within the boundary of the contact surface. So it means that the force being subjected to the crate will not cause the crate to tip. Now that we are clear with that, so we can proceed with the next part of the analysis. Okay, based on the solution strategy that we have defined earlier, our second step is that we need to find the maximum static friction limit or the value of Fs. Okay, Fs can simply be calculated by multiplying the coefficient of static friction mu s with the normal force. Okay, given that mu s is 0.3 and the magnitude of the normal force tadi dah kirakan, which is this one, it is 236.2 Newton. So you can easily calculate the value of Fs to be 70.86 Newton. So what does it mean? Okay, look back at our solution strategy tadi. Dia kata if F or the friction force is less than the Fs, the friction limit, then we can say that this object is in equilibrium or it will not move. Okay, now we compare the value of F that we get, the friction force that we get, with the friction limit. Okay, so our F is 69.2820 Newton, whereas the Fs that we get is 70.86 Newton, which is, in a way, our F is less than Fs. So based from this calculation, we can prove that the crate will not slip and it will maintain in equilibrium, meaning that the 80 Newton subjected to it will not cause the crate to move. So that is how you prove the state of the object subjected to a friction force. Okay, as I've reached the limit of this so-called short video series, so I'm going to continue demonstrating the following example in another short video. Okay, so see you later, alligator.